Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Sample problem 5.9. The statement is given that for the beam and loading shown, determine the equation of defining the shear and bending moment at any point, and the second part is shear and bending moment at points C, D and E. So this is the beam and the loading is shown. This is a simply supported beam with a uniform linearly varying load from point A to C, and then uniformly varying load that is decreasing from C to B. So it is given in part A that you have to find a equation that determine the shear and bending moment at any point. So you have to find out the shear force equation and bending moment equation, a single equation. So to find out the shear force and bending moment at any point. So definitely there will be a single shear force equation and bending moment equation from which you can find out the shear force and bending moment at any point in the beam. Again, note that there is nothing given to solve this problem using singularity function, but it is given that you have to find out the equation for bending shear force and bending moment in order to find the shear force and bending moment at any point. So definitely we will solve it by using singularity function. Next point is that if we get the shear force and bending moment equations, then we can find out the shear force and bending at point C and E. So let's solve this problem. For first of all, for solving this problem, you have to find out the reaction forces at point A and at point B. So RB and RA, you have to find this, and you must be able to know how you will find the reaction forces at point B and point A. So I will just give you a clue that you can see that this is a uniformly varying load from point A to point C. Again, if you want to convert it to concentrated load, so it will be equal to half of W naught into its total length, and the total length from point A to point C is L by 2, because L by 4 plus L by 4 is L by 2. So this concentrated load will be acting, let's say, at this point. So and this will be equal to 1 over 4 W naught into L. Similarly here it will be again the same, and this will be this linearly varying load will be converted into half of 1 over 4 into W naught into L. So now you have the beam like this. This will be the reaction forces. This will be a concentrated load, and this will be again concentrated load. It is 1 by 4 W naught into L, and it is also 1 by 4 W naught into L. The length is given 1 by L by 2, and again the length is given L by 2. Now you can use the equilibrium conditions to find out the reaction forces at RA and RB. So when you solve it, so your RA will be the same, that is 1 over 4 W naught into L, and RB will be also 1 over 4 W naught into L. After finding the reaction force, you will use singularity function in order to find the shear force equation and bending moment equation. So these are the same things. So let's solve this. You can see the reaction force is represented as 1 over 4 W naught into L, and the reaction force at point B is 1 over 4 W naught into L. Again, if you look at the figure, so this scenario is also not available in this loadings. The only scenario is available like that. So you have to close this triangle. So you have to extend it in order to close it. So it is, let's say this was L by 2. So again you have to close it through again L by 2. So if you take it to this point and close the load, so W naught is up till L by 2, so 2 W naught will be for whole length, for this total length of the beam. So let's say we will convert this like this, and again from this point you will have to given opposite. This will be also 2W naught, but it will be positive because it will be upward in order to cancel the effect. Now you can see we have converted this loading into this type that is shown over here. Initially it was like this. We have extended W naught to total length, which is equal to 2W naught, and there is this has been converted to this, which is shown above. Now you can see the scenario is available in the loading. So this is the same scenario. So this loading, at this loading, if you go back to this same thing. So for first loading the A will be 0 for above, and for the below it will be, for this loading here A will be equal to 0, and for this loading this A will be equal to L by 2. Again, if you look, let me write again this thing as well. For this loading we can see that shear force equation is equal to minus K by 2 into x power 2, x minus A power 2. So let me write it minus K over 2 shear force is equal to minus K over 2 into x minus A ki power 2, and the bending moment will be equal to minus K over 3 into x minus A ki power 3. Let me confirm it as well. Oh, this is minus 6. This is minus 6, because if you integrate it, it will be 3 divided by 3, which is 6. So now we will use this equation. So in this case you can see K, we will find K for this as well as K for this. So slope for this line will be equal to this height, which is 2W naught, and divided by 2 base, which is length. So slope for this will be 2W naught over L, while slope for this will be equal to 2W naught divided by this length, and this length is L. So this slope will be equal to it is like this. So that is minus 2W naught divided by L by 2, which will be equal to minus 4 into W naught by L. So slope for the upper line K1 will be 2W naught over L, while K2 for this will be 4W naught into divided by L. So we will use this shear force linearity equation and bending moment to find out the shear force equation and bending moment equation. So you can see that as Vx is equal to minus K over 2, let me erase something so that it will be easily visible. So again you can see that this V shear force for this scenario will be equal to minus K over 2 into x minus A whole square for this loading, and this will be minus K over 2 into x minus A whole square. Now for first scenario, A will be equal to 0, that will be minus K over 2 into x minus A is if A is equal to 0, so it will be x whole square minus K over 2. In this scenario, this A will be equal to L by 2 for this loading. So that will be x minus L by 2 whole square. Again, this K is equal to 2W naught over L, so that will be equal to minus 2W naught divided by 2L into x square and x square minus k over 2. This k2 will be, let me write its value, it will be minus 4w0 over L into x minus L by 2 whole square. So this is the shear force equation for this beam. Similarly, you can also find out the bending moment equation for this beam. Let me show you this. Let me clear this all these values. So you can see that now the beam will be this. This is how this load has been converted into this. Now the actual beam will have a reaction forces at both ends as well, and the beam is transformed into a new type of loading. Always remember that we will take the reaction forces or any forces that is available on the left side, because on right we start drawing the sections, or we move from the left side to the right side. So anything on the right side will be neglected. So the loading equation for this type of beam, again if you move back, I will also clear this so it will be easy for us to move quicker. Erase all. So you can see the loading equation for this uniformly linearly varying rod is Wx is equal to k into x minus 1 power 1. So it is the same. This Wx will be equal to, for upper loading it will be k1 into x minus, let me write Wx is equal to minus k, it was minus, or it was positive in the equation. Let me show you, it is positive. So that is equal to k into Macaulay bracket x minus a ki power 1. So this was the general equation. Now there are two loadings, so that will be w into x, k into x minus 1 plus k into again x minus a ki power 1. So for this first loading, a will be equal to 0. So that will be equal to k1 into x minus 0 power 1 plus k2 into x minus. For this loading, a will be L by 2. So that will be x minus 1 over 2 L power 1. So x minus 0 is equal to x, and power 1 will be equal to k1 into x, and the slope of this was 2w0 over L. So this will be 2w0 over L into x plus k2 is minus 4w0 over L into x minus 1 over 2 L. So this will be the loading equation. Then we will move toward the, this is further simplified. So that is 2w0 L over x, this is the same which I have written, and that is minus w0 over L into x minus L. This is the loading equation for the given beam. Again, the shear force equation will be, I have written again, that is Vx is equal to minus k over 2 into x minus a ki power 2. Let me check it. The shear force k minus k by 2 into x minus a ki power 2. Again, so for both the load, again initially neglect this. So this is for concentrated load. There is a concentrated load at the start as well, so we have to encounter it as well. So Vx minus V0 is equal to minus W0 into L, W0 over L into x square minus 2 W0 over L into x minus 1 over 2 L whole square. So this was the general equation for the shear force. So if you use the second term, so that is also minus k over 2 into x minus a whole square. For the first loading where where a is equal to 0, so if you put a is equal to 0, that will be minus k over 2 into x square, and that will be minus k over 2 into x will be here, x minus a will be L by 2, which is x minus L by 2. Similarly, if you put the value of k, which was 2 omega naught over L, and k2, which is minus 4 omega naught over L. So if you solve this, so this will be minus w naught L over L into x square minus 2 w naught L into x minus 1 over 2 L square. Again, shear force at this point is 1 over 4 into w naught into L. So you have to take it as well. So when it will go to the right side, so it will be, this term will for the linearly varying load, and this will be a concentrated load. Again, if you do not want to write V naught, so you can write the equation for this, and at the last you can also use the shear force equation for the concentrated load. So you can see, let me show you it as well. So you can see load for the concentrated is minus P into x minus a ki power 0. So at that condition where the load is at this point, so a is equal to 0, so it means x minus 0 is equal to x, and x anything power 0 is equal to 1. So in that condition, Vx will be equal to minus P, and the P was minus 1 over 4 W naught into L. So we have written minus W naught, so when it moves minus 1 over 4 W naught into L. Again, so since the force is positive, so you have to take it positive. So that's why if you do not interested to write it as V naught, so you can at the end you can place its function for the shear force for concentrated load. Also, the shear force at this point A, the shear force will be 1 over 4 W naught into L, but the moment at this point will be 0, and the moment will vary if you move along the length of the beam. So this is the shear force equation for the beam as shown. Similarly, the bending moment equation can also be found, and you know that the equation of bending moment will be equal to minus k over 6 into x minus a ki power 3. That is given, that is taken from this loading. Minus k over 6 into x minus a ki power 3. So you have, this is for loading 1, and this is minus k over 6 x minus a ki power 3 for loading 2. For loading 1, a is equal to 0, so that will be equal to minus k over 6 x cube, and for loading 2, that is x will be L by 2, a will be L by 2, so L by 2 ki power 3. And again, if you put the value of k for first loading, that is 2 W naught over L, and K2 is minus 4 W naught over L in this equation, so it will be the same like this. Also, you can see due to this concentrated load at point A, the moment equation will be minus m naught into x minus a power 0. So if a is equal to 0, so mx will be equal to minus m naught into x power 0, and x power 0 is equal to 0. X power 0 is equal to 1, so mx will be equal to minus m naught. Clear? And this m naught will be again, sorry, I have used this, not this, you have to use this equation, because the bending moment for the concentrated load is minus px, so do not consider this. So x is equal, a is equal to 0, so it will be m of x will be equal to minus p into x power 1, and x power 1 will be x. So my and p was 1 over 4 w naught into L and x. So movement due to concentrated load when you move from this point, from this point will be 1 over 4 w naught into L x. So if you put all the values, so mx will be equal to minus m naught. This is the movement due to the concentrated load, and that is equal to, if you put the k1 and k2 over here, so this equation will be like this. Clear? The moment at point 0 is equal to 0, and the function of movement due to concentrated load is this. Clear? Which is given at the end. So mx will be equal to this equation. So this is the single bending moment equation for the loading, and this is the single shear force equation for the loading, and this is drawn. But before drawing this, let me clear that we have solved our first part of the problem, that is to define a single equation for the shear force and bending moment, or the equation from which we can find out the shear force and bending moment at any point in the beam. So you have to put the value of x at any point of x. You can calculate the shear force and bending moment. So this was the first part. Now for second part, in second part we have been asked to find out the shear force and bending moment at point D, at point C, at point E, and at point B, because C, D and E are given. So we will now look into that. So this was the basic equation. Let me delete all this thing in order to have a clear visibility. So this is the shear force equation, and this is the bending moment equation. Now for shear force at point C, for example, so C is at a distance of L by 2. So if you put L by 2 over here, clear? So this L by 2 will be cancelled with this, so this term will be, the second term will be 0, and here similarly the second term will be equal to 0. So again, not here, this is the single equation, so this will be 0, and the remaining is given over here. So you can see at point C, if this will be 0, and if this will be minus w naught L square over 4L, and this is 1 over 4 w naught into L. So if you calculate, or if you simplify, it will be minus 1 over 4 w naught into L, which will be cancelled with this. So shear force at point C is equal to 0. Similarly, bending moment at point C at L is equal to 1 over 2. So if you put L 1 over 2, so this term will be equal to 0, and the shear force bending moment equation will be this, and if you further solve it, so shear bending moment at point C will be this. Similarly at point D, now you can see that point D is at a distance of L by 4, which was given earlier, so L by 4. So if you put, let me again erase all. So now for x at point D, this distance is L by 4. So if you put L by 4 over here, so if you subtract L by 4 from minus 1 over 2, it will be negative value, and anything inside the Macaulay bracket which is negative will be considered as 0. Similarly, this term will be also 0 in the bending moment, and when you solve this, so you will have shear force at point D and at point B, and bending moment at point B as this. At point E, if you put x is equal to 3 by L, so definitely this value will be positive, this will be positive, and this, and again this. So if you solve this, so the bending shear force at point E will be this, and the bending moment will be this. Now you have to plot them on the shear force. So at point A, you can see there was a shear force which is 1 over 4 W naught into L. Clear? Let me show you at point A there is a shear force. Now at point C, at point D, C and E, you have to determine this. So let's start with point C. So at point C, you can see that uh, shear force was 0. So shear force at this point 0. At point D, it was 3 over 16 into W naught into L, which is a positive value, and if you plot it, it will be like somewhat here. And as this shear force is second degree equation, so it will be a curve in the clockwise direction. Similarly, at point E, this is a minus 3 over 16 W naught into L. So this is 3 over 16, so again this will be minus 3 over 16, and you have to locate this. And at point B, the shear force will be the same as the 1 over 4 W naught. So you have to join them, and this will be a second degree curve or parabolic, and it will be like same. So this is the shear force diagram for the. So at point D you have calculated the shear force, at point C it is 0, and at point E it is minus 3 over 16 W naught into L. Now for bending moment diagram, as we know that at point A shear force is 1 over 4 W naught into L, but at point A there is no bending moment. At point D the moment is a positive value, which is 11 over 192 into W naught into L, as it is general. So if you have W naught and L square value, you can made it precisely. So at this point, from point A to C, it will be again a curve here, because it is cubic, so it will not be a straight line, it will be a curve. Again it will be a curve. At point C, you can see at point C the moment is greater than point D, 1 over 12 and 11 by 192. So this value is greater, so it will be above. So if you plot it, it will be somewhere at point C, it will be like this. Again this is a cubic, so it will be curve. Now at point E, the load is minus 3 over 16, and it is at point E, this is ME, which is 11 by 192, and it is same as D. So you can easily take this point. You can easily, let me choose the marker. So at point at point D and E, they have the same, which is 11 by 2. So you can project that point, and this will be your bending moment between point C and D, which is cubic. And similarly at point D, there will be no shear force, so it will be 0. At point B, there will be 0, and this will be also a curve. So this is the shear force and bending moment diagram, and we have calculated the shear force at point D and bending moment at point D, shear force at point C and bending moment at point C. Similarly, the shear force at point E and bending moment at point E. And these are the value of shear force and bending moment at their corresponding points. I hope you have enjoyed the videos. Now it's your duty to solve problem 5.108 and problem 5.104 on the basis of singularity function. Thank you for watching the video. If you like the videos, kindly subscribe, like and watch. Thank you.